Hello everyone, in this video we're going to be looking at the second part of section 8.3 and this is integrals involving powers of secant and tangent. So we're going to figure out how to solve integrals of the form secant to some power times tangent to another power. So again, we're going to look for combinations of trig integrals. We're trying to break them up so that we can have some inside function inside of a power function so that its derivative is seen on the outside, so that way we can apply U substitution for the power rule, right? So we're trying to save the derivative of some inside function on the outside. Okay, so when the power of secant is even and positive, what we're going to do is save a secant squared factor. And the reason is because we're going to convert all of the rest of the secant factors into tangent factors, and then the inside function will be tangent, and we'll have left a secant squared, which is the derivative of tangent, right? When the power of tangent is odd and positive, what we're going to do is save one secant tangent factor, because we'll convert all the other tangent factors to secants, so that secant will be the inside function, in which the derivative of secant is secant tangent. So if there are no secant factors and the power of tangent is even and positive, we're going to convert the tangent squared factor to a secant squared factor and then expand and repeat if necessary. So that's very similar to, I think, method 3 or guideline 3 for the sine and cosine. So if the integrand is of the form secant to some power, so in other words, if there are no tangents and m is odd and positive, then what we're going to do is use integration by parts. Right? We did a problem like this in the last section. I think it was secant cubed, and so we saved us one secant on the outside, or one secant to be one of our factors, and secant squared to be our other factor, and we use integration by parts. Right? And then when the first four guidelines don't work, try converting things to sine and cosines and see if things cancel out, so you can get something that you know how to deal with. Okay, so one thing we need to remember here as far as our trig identities go is that tangent squared x is equal to secant squared x minus 1, right? And also secant squared is equal to tangent squared x plus 1, right? So that is our trig identity, which comes from the original Pythagorean trig identity here. If you divide everything by sine, or actually, sorry, divide everything by cosine, you would get this. Okay, so the power of tangent is odd and positive. What are we going to do? Tangent is odd and positive. That's guideline 2. We're going to save a secant tangent, right? So to save a secant tangent, we're going to rewrite this as, first let's just rewrite it, so with the secant, the power of secant up in the numerator, right? So this looks like tangent cubed x, and then secant x, and if it's a square root in the denominator, it would be negative 1/2 x dx. So now we're going to save one factor of secant tangent. So I'm going to factor out a tangent, so I'd be left with tangent squared. If I pulled out a secant x out of secant to the 1/2, then I'd be left with secant x to the negative 3/2, right? Because then if I multiplied secant to the negative 3/2 times another secant, I'd be back to where I started from, which is secant to the 1/2. So that leaves me with my tangent x, secant x on the outside, just like I wanted. Right? And so now what we're going to do is we're going to convert the remaining factors to secants. So notice I have a tangent squared here, so I can use my trig identity that tangent squared is equal to secant squared minus 1 times secant x to the negative 3/2 tangent x secant x dx. So now I'm going to distribute my integral sign. Whoops, distribute my integral sign to the secant, try it again, to the secant and to the secant squared and to the 1, and I'm going to distribute all of this to both terms as well. All right, so all in one step. Secant squared times secant to the -3/2. Remember, when I multiply those, I add their exponents. So if I add their exponents, I'm left with secant x to the 1/2 tangent x secant x dx, and now minus, because it's -1, secant x to the -3/2 secant x, or I'm sorry, tangent x secant x. Pull this over a little bit so I don't run out of room. Tangent x secant x dx. Right? So now each one of these is going to be a u substitution with u equals to secant x, because the derivative of secant is secant x tangent x, or tangent x secant x. Right? So the derivative is perfectly on the outside. So here's where I can do my little cheat rule, where I think about my inner function being secant, and I take the derivative of like that inner function u to the 1/2. All right? So if I had u to the 1/2, then I would add 1, which would make it 3/2. So I need to divide by 3/2, which would be 2/3. Leave that secant x on the inside alone, the 3/2, and again, I don't have to chain anything on, because that we're undoing the chain rule, and that tangent x secant x would have been chained on in order to get above. Remember, you can always go backwards from, if I'm claiming that this is the antiderivative of there, I can take the derivative of this, and I will get secant to the 1/2 times tangent x secant x. Right, you can always check yourself. Okay? And then I get minus, now -3/2. What I'm going to do, I'm going to bump up the power by 1, so that gives me -1/2, right? But I'm going to divide by -1/2, in other words, multiply by -2. So this is secant x to the -1/2. And again, nothing else goes there, and then plus c, right? So here I get 2/3 times secant x to the 3/2 plus 2 times secant x to the -1/2 plus c. Right? And again, the best thing about integrals is that you can always check your work, right? If you took the derivative of this with respect to x, you should get tangent cubed over the square root of secant x. You might have to do some algebra to get it back that way, but you should get that exact answer. Right? Okay. So now let's look at a different example. The power of secant is even and positive. Right? If the power of secant is even and positive, then what we need to do is we need to save a secant squared. Right? So even though there's a 3x on the inside, we can still just treat it as if it were just like x on the inside, except when we go to take the antiderivative, we'll be a little bit more careful. Right? So here, I'm going to write secant to the 4th of 3x times tangent cubed of 3x, and then I'm going to write my factor of secant squared of 3x that I'm saving, right? This is what I'm saving for my derivatives when I do the u substitution, right? And so now I'm going to convert this secant to the 4th to a secant squared, so that way I can, if it was secant to the 4th, this should be secant squared. Right, so secant squared times secant squared gives me secant to the 4th. Right, so I convert this secant squared into a tangent. So remember, secant squared is equal to 1 plus tangent squared. And I just have to make sure that the inside of the function stays the same. Right, so secant squared can be written as 1 plus tangent squared. And then since that was 3x, the inside function of this has to be 3x. and then we multiply that times tangent cubed of 3x, and then secant squared 3x dx. So again, in this step, I'm going to distribute the integral to both terms, and I'm going to distribute all of that to both terms, right? The tangent cubed and the secant squared. So I end up getting tangent cubed of 3x secant squared of 3x dx plus the integral of tangent to the fifth of 3x and then secant squared of 3x dx. Okay, so to solve these integrals, we have, again, you can do them, they're u substitutions. And my inside function is going to be tangent, right? Because this time it's going to be tangent of 3x, right? Because the derivative of tangent is secant squared. But we have to remember to be a little bit careful here, because remember when I said, okay, if I want to take the antiderivative of, say, let's do sine of 3x. Well, remember now, instead of multiplying by 3 on the outside, if I were taking the derivative, I would divide by 3. So this would be negative 3 cosine of 3x plus c. Right? So we've got to keep track of that also when we're doing this u substitution as well. Right? So I'm going to do this the quick way, but again, if you can't follow, you can go ahead and do u substitution with both of those and you'll get the same answer. Right? So I see it's my tangent function cubed. Right? So first I need the 1/3 because of what I was just talking about, because there's a 3x there. So I need the 1/3, and then I also now it's u to the 1/2, or I'm sorry, u to the 1/2, u cubed. So now I need to bump it up, so it'd be 1/4 u to the 4th, but here it's tangent of 3x to the 4th. Right? And then here, what do we get? We get, again, we need to have a 1/3 out front because, because of the 3x there. And then I need to pretend like it's u to the 5th. So this could be 1/6 u to the 6th, but u is tangent to the 6th of 3x and then plus c. So now I get 1/12 tangent to the 4th of 3x plus 1/18 tangent to the 6th of 3x plus c. Okay. So now let's look at another example here. This is when the power of tangent is even and there's no secant. Right? So first we're going to need to find the antiderivative, and then we'll plug in our limits 0 to pi over 4. So what we're going to do is we're going to realize that tangent to the 4th is the same as tangent squared x times tangent squared x dx. Why? Because now I can change one of those tangent squared x to secant squared x minus 1 dx. Right? So now I can distribute, and if I distribute, I end up getting tangent squared x secant squared x minus tangent squared x dx. Now this portion of it is done. This is a u sub with u equals to tangent x, right? Because remember the inside function, if it's tangent, then the derivative that we see on the outside is secant squared. This guy up here, this tangent squared, I can once again use the Pythagorean identity, right? So this guy right here, we're going to leave alone, and I'm just going to say this is tangent squared x secant squared x dx, and then subtract. And now instead of tangent squared, I'm going to write secant squared x minus 1 dx. All right, I'm going to use the Pythagorean identity. Okay, so again, this one's a u sub, so tangent's on the inside, so it's like u squared. So I do 1/3 and then tangent cubed x, and again, there's nothing else because the derivative on the outside is there, minus, now I'm going to take the antiderivative of secant squared, right? And the antiderivative of secant squared is easy, right? What function has the derivative equal to secant squared? Well, that's tangent of x. And then minus what's the antiderivative of 1 is x. If we're careful with our negative signs, we will get the right answer. Which is that. But now what did the problem ask? The problem asked for the definite integral, right? From 0 to pi over 4 of our original function was tangent to the fourth of x. So we found its antiderivative to be 1/3 tangent cubed of x plus, minus tangent of x plus x. And now instead of plus c, we're going to evaluate this from 0 to pi over 4. Tangent of pi over 4 is 1, so this is 1/3 times 1 cubed minus tangent of pi over 4 is 1 plus pi over 4. And then minus tangent at 0 is going to be y over x, so 0 over 1, so that's just 0. So this is 1/3 times 0 minus 0 plus 0, so that's all zeros. So I ended up getting 1/3 minus 1, which is 2/3, or I'm sorry, negative 2/3 plus pi over 4. Right, which is approximately 0.119. Okay, so that's how you do secants and secants and tangents. The same strategy works for cosecants and cotangents, right? You just have to use the identity of cosecant squared x, I think, minus 1 equals cotangent squared x. Might be a plus, I can't really remember. But if you manipulate that first trig Pythagorean identity, you can get the corresponding trig identity that you need here. So if you ever get cotangents and cosecants, you can still follow the same methods that we just looked at. So remember, the final strategy that we had was if nothing else works and it doesn't look like any of the ones before it, right? So if it doesn't look like 1, 2, 3, or 4 guidelines, then the last thing we can do is try converting to sines and cosines. Right, so this last example is one where I don't have anything that looks like any of those first 4 guidelines, so I can work at converting to sines and cosines. All right, so I'm going to rewrite this as secant x times 1 over tangent squared. So dx. But what is 1 over tangent? 1 over tangent is, well, actually, let's write this first. 1 over secant is 1 over cosine of x, right? And 1 over tangent is cotangent squared x dx, right? So now I get 1 over cosine of x. And now what is cotangent? Cotangent is cosine of x over sine of x squared dx, right? It's tangent flipped upside down. So now I see that I get one of these cosines cancels out with that one, so I'm left with just a single cosine on the top, and a sine squared on the bottom, right? So now if I think about sine being my inside function, then that means that the derivative of that inside function is cosine, which I see right here. All right, so maybe a better way to look at this would be cosine, or let's write it as sine x to the negative 2 cosine x dx, right? So again, this is going to be a u sub with u equals to sine x, because the derivative of sine x is cosine x, which is perfectly right there, right? So here I treat this like u to the negative 2, so that would be negative 1, and then instead of u, our function is sine of x to the negative 1 plus c. So this looks like negative 1 over sine x plus c. But what is 1 over sine? Well, that's cosecant. So this is negative cosecant x plus c. Right? So again, when all else fails, try converting to sines and cosines, and maybe you can get something that's easy to deal with like we just did there. And again, I was going through those u substitutions fast. Hopefully at some point, once you practice this enough, you'll get good enough to be able to do it like that. But again, if it's not making sense, please just go ahead and do those u substitution integrals as side work, and you'll be able to get the correct answer. All right, thank you.